Hello everyone, welcome to SPEC eLearn, the online learning channel dedicated to chemical engineers. Tray column internals, types, applications and selection. In this video course, you will learn what are column internals, the steps in tray column design and the impact of types of trays in the tray column sizing, types of trays and downcomers and their roles in tray columns. I would appreciate if you subscribe to the channel. We are striving hard to deliver valuable knowledge content for your career progress. So subscribe now before you forget. Tray columns are widely used for distillation or absorption in refineries, petrochemical plants, process plants, and oil gas industry. Tray is a device that provides contact surface for mass transfer between liquid and vapor. In any conventional tray, vapor rises through a pool of liquid on the tray deck and then disengages from the liquid in the space above the deck. Liquid enters a tray from a downcomer above and leaves to the next tray via a downcomer below. Conventional tray has three functional zones. This sketch explains the three functional zones. 1. Active area for mixing vapor and liquid. This is the zone where mass transfer occurs. 2. Vapor space above the active area. This is the zone in which liquid is separated from the vapor. 3. Downcomer between the trays. This zone has two functions. First, moving liquid from one contacting tray to another, and second, disengaging vapor from the liquid. Each of these zones takes up a vertical and horizontal space in the tower. A typical tray column with the vapor-liquid flow traffic is shown in this figure. The vapor moves up through the holes and the liquid flows across the tray and flows over the wire into the downcomer. In this figure, you can see the three functional elements within a tray tower: the contacting tray, the phase separator, and the downcomer. In the normal operation of trays, the liquid phase is continuous and the gas bubbles through the liquid. This is known as froth regime. Steps involved in the design of tray column. Design of tray column is a two-step process. Step 1 is the process design. In this step, you determine the number of theoretical stages, estimate the stream flows including the reflux ratio and hue duties of reboiler and condenser. Step 2 is the mechanical design of column. This is all about the hardware of the system needed to accomplish the separation process. The hardware are the tray internals. The steps in tray column design are: select the type of tower internals, calculate the tower diameter, determine the tower height, estimate the column cost. This phase has a major impact on the column cost. The choice of internals greatly influences all costs, including the column, the structures, connected piping, auxiliaries such as reboiler, condenser, and control instrumentation. Hence, understanding the type of internals and advantages and their limitations is part of the design process. Those who operate the plant, it is equally important to know your equipment so that you can evaluate its performance. Classification of trays. Trays may be divided into two major categories: cross-flow trays, counterflow trays. Cross-flow trays get their name because liquid flows across the tray through the downcomer, while vapor rises through the perforation in the tray deck. In countercurrent trays, the vapor moves vertically up and the liquid moves vertically down. That is, they flow in the opposite direction. The most commonly used type of tray is the cross-flow trays. What are the various types of cross-flow trays? We will move on to find out. There are three types of cross-flow trays in common use today. They are bubble cap trays, sieve trays, valve trays. Bubble cap trays. Bubble cap tray is a flat perforated plate with chimney-like pipe called risers around the holes. The risers are fitted at the top end with inverted cup-like caps having slots around the surface through which the vapor flows out. Shown in this figure is a figure of a bubble cap tray. Liquid and froth are held on the tray to a depth at least equal to the wear height or riser height, giving the bubble cap tray a unique ability to operate at low vapor and liquid rates. Bubble cap tray comes in varieties of shapes and design. Figure B shows a typical cap commonly used in the industry. Today, sieve trays and valve trays have replaced bubble cap trays as the most preferred choice due to their relative advantages. Only special applications still use bubble cap trays. Sieve trays. Sieve tray is one of the most commonly used mass transfer contract devices in the industry. Before we move on, I would like to make a call to my dear viewers. Your SPEC e-learn channel is one-stop learning and skill development destination for your career needs. Get instant access to useful career-oriented subjects and become knowledgeable and competent. So do not forget to subscribe. Please press the subscribe button now. This figure is an illustration of a typical sieve tray. The sieve tray is a flat perforated plate. Vapor issues from the holes to give multi-orifice effect. The vapor velocity keeps the liquid from flowing down through the holes. Note, the trays are segmented. There are 6 tray segments. They are fabricated in several small segments as shown. The reason is that the tray in one single piece cannot be taken inside the tower because of the size. They are assembled inside the tray. Note the wear plate numbered as 7, which is bolted to the tray. The liquid from the tray overflows the wear to the downcomer. Sieve trays are simple and easy to fabricate and therefore relatively inexpensive. Sieve trays are widely accepted as a low-cost mass transfer device where high turndown is not required. Dual flow trays. Dual flow tray is a sieve tray without a downcomer. It is designed with enough open area on the tray deck to eliminate stagnation and promote backmixing. Vapor moves up to the tray above through the hole while liquid flows down through the same hole. That results in more distribution and low efficiency. Dual flow trays have capacities similar to packing. Dual flow trays are well suited for fractionation of polymerizable compounds, fouling services, slurries, and corrosive services. Give more bubbling area and therefore have a greater capacity than other tray types. Dual flow tray is also the least expensive to make and easiest to install and maintain. Dual flow tray have poor 10-to-1 ratio, resulting from the rapid fall off in efficiency as the vapor loading decreases. Therefore, the operating vapor and liquid rate ranges must be kept small. Valve trays. Valve trays in advanced tray technology and finds very wide applications in refining, petrochemical and process industries. Unlike bubble cap trays and sieve trays, which have fixed openings and hence fixed area for vapor flow, the valve trays, as the name suggests, have variable area for vapor flow. Valves can be round or rectangular. The valve discs rise as vapor flow rate is increased. Restrictive legs at the bottom of the valve unit control the upper limit of opening. As the vapor flow is reduced, the valve opening is reduced, or they may settle at intermediate position over the holes. This stops the liquid from weeping through the opening and gives valve tray its most important advantage: good operation at low flow rates and therefore a high tan down. When there is no vapor flow, the valves lay flat on the tray floor. The valve units are designed in various shapes such as round, rectangular, fixed and movable or floating valves. Each shape and design is selected for a specific service requirement. As seen in the figure above, there are two types of round valves available: conventional, that is uncaged, and caged valves. The rectangular valves are oriented parallel to a liquid flow direction, providing lateral vapor release and a closed upstream edge to minimize weeping. This contributes to an improved efficiency or capacity profile compared to conventional round valves. Fixed valves do not move and combine the effect of attributes of sieve holes and float valves and offer low pressure drop while delivering high tray performance in terms of capacity and efficiency. Fixed valves are available in two shapes: triangular and tapered rectangular. Valve trays require considerably less material for construction and less expensive to fabricate compared to bubble cap. Compared to moving round valves, rectangular valves need less metal as it generates less scrap during fabrication. Cartridge trays are used for small flanged columns having diameters in the range of 300 to 800 mm, where physically installing the trays inside the column is not feasible. Note that conventional sieve trays and valve trays require man to go into the column to install the trays. In small trays, this is not practical. This figure is an illustration of cartridge tray. Cartridge trays are assembled in bundles for easy and fast installation. They can be equipped with all types of tray decks, sieve or valve, and downcomers. The fully assembled cartridge trays are lowered into the shell from the top. The gap between the tray cartridge and the column shell is eliminated by fixing a lip seal made of Teflon to the tray deck. This is essential to prevent vapor bypassing of the tray through the gap. Tray design variables. Active tray area or bubbling area and tray spacing are two important design parameters for tray column, which will significantly impact the column size. Unlike pack tower, where the entire cross-section of the tower is occupied by packing, tray column design needs thoughtful insights with respect to active area of the tray and the downcomer. Also, adequate space needs to be provided for vapor-liquid disengagement to prevent entrainment to the tray above. The tray design variables are as follows. Tray design variables which will impact the three different sections of the tray are, for the tray, flow length, vapor liquid rates, active area, liquid holdup, and pressure drop. In case of phase separator, physical properties and length of the separator. In case of downcomer, a liquid froth rate and pressure drop. Each of these variables will influence the selection of type of column internals and tray layout parameters for specified process application. That emphasizes the fact why understanding the tray internal is important before you begin the design process. Comparison of the tray types. The type of tray to be selected for any given application is the first and foremost important step in the design of tray columns. The initial cost of the tray depends on the type of tray design. Tray selection criteria are a range of operation, pressure drop, fouling and maintenance, entrainment and efficiency, ease of fabrication, and cost. We will compare bubble cap, sieve, and valve trays with these criteria. Dual flow tray is not commonly used and hence not included in this analysis. Range of operation or stand down. Of the above criteria, most important parameter is the ability of the tray to deliver stable operational performance over a wide range of capacities. Depending on the nature of the fluid handled and the operational flow rates, the performance of each of the tray discussed above will vary. For instance, bubble cap trays are the most suitable for extremely low flow applications. Valve trays deliver superior performance for operation over a large capacity range. For extremely low turn-down ratio and extremely low weeping rate at low flow rates, bubble cap trays are the obvious choice. For R&D services, where the quantum of flow is extremely low, the bubble cap tray is the most suited. Where does the sieve tray stand in terms of this criteria? The major disadvantage of sieve trays is its inability to perform at optimum efficiency at low capacities as compared to valve trays for a given application. Thus, the operating range or turn-down ratio of the tray has become important parameter as the criteria for selecting the trays. Next criteria, entrainment and efficiency. Sieve trays and valve trays have comparable capacity, efficiency, entrainment, and pressure drop at higher throughput. Tapered rectangular fixed valve trays can handle higher throughput at a given liquid load than sieve tray due to later release of vapor. Refer to the figure shown earlier. For the same reason, the rectangular fixed valve trays have lower entrainment and higher efficiency. Next criteria is fouling and maintenance. Fouling is an important factor while selecting tray device. Fouling will lead to reduced capacity and increased maintenance for cleaning. Fouling may be caused by presence of solids in the feed, such as slurries, or formation of polymers or reaction products during operation inside the column. In some processes, the solids in the feed may be carbon powder coming from upstream processes, such as reactors. Where does the sieve tray stand in terms of this criteria? Sieve trays with a large diameter have superior fouling resistance compared to moving valve trays. Fixed valve trays has almost similar fouling resistance as sieve tray. Sieve trays require the least maintenance. The bubble cap trays have high tendency to fouling due to settling of solids in the space on the tray just below the slots in the caps. The settled solids cannot be removed on line. Hence, these trays need increased maintenance if used in fouling services. Next criteria, ease of fabrication and cost. Ease of construction of the tray influences the cost of manufacture. The sieve tray is simple in design and the easiest to fabricate of all the three trays. Considering the design aspects with detailed dimensional requirements for slots, caps, etc., the fabrication of bubble cap trays is relatively difficult, and that makes them more expensive to make. The ease and cost of fabrication of valve trays lies between the two. Based on this criteria, sieve trays are the cheapest of all the three. Valve trays are more expensive, and bubble cap trays are the highest in terms of cost. For most industrial applications, either sieve trays or valve trays are the preferred choice. Higher turn-down ratio and cost of energy saved at low capacities when the plant is required to operate under certain circumstances drive the selection of tray in favor of valve trays over sieve trays. These performance factors justifies the slight cost difference between the two. Pressure drop. Pressure drop is another factor to be considered while selecting the type of tray. Pressure drop is usually specified by the user based on the process requirement, as column is part of the process network. Typical tray pressure drop per tray are as follows. Conventional tray 8 millibar. Low pressure drop tray 3 to 4 millibar. Based on the user requirement, the tray supplier will supply suitable trays. Bubble cap trays have higher pressure drop as compared to sieve trays and valve trays. Sieve trays and valve trays have comparable pressure drop. Types of downcomer. Next important step in the column internal selection is to decide on the type of downcomer. Here again, the type of service is most important driving factor. Downcomers are of two types. Standard downcomer, sloped or truncated downcomer. Shown in this tray is a tray fitted with standard downcomer. Standard downcomer is one in which the width of the downcomer at the mouth where the froth exits the tray is the same as the width at the bottom. For most of the applications in refineries and petrochemical plants, oil and gas processing units, standard downcomer is commonly used. This figure illustrates a sloped downcomer. Note that the large area at the DC entrance, that is the mouth, which helps to reduce the velocity, suitable for foaming liquids in special applications. Another application where a truncated downcomer is used is to increase the capacity of the existing tray with standard downcomer. By removing the existing standard downcomer and fitting it with a truncated downcomer, you increase the area for the tray at the bottom and thus increasing the capacity of the tray. Please subscribe to our channel and get updates on the upcoming courses by pressing the subscribe button. It will motivate us to produce free, knowledge-rich video content for you. With this, we have come to the end of the presentation. Please give your comments, if any, about this course after you finished viewing this video. Share with your friends and colleagues to reach out to large number of career-oriented professional students. Thank you for watching.